A very good morning to Dr. Sakina and Dr. Azmin. We are from Group Hartalega and we are going to present a SIR model for dengue fever disease among hosts, which is a simulation for Sarawak, Malaysia. Our group is made up of 5 members, which are Xin Yu, Koh Jun Xian, Lim Yin Shiuan, Koh Jun Xian, and I, Lim Jing Yi. First of all, in Malaysia, dengue fever is generally an urban disease that transmitted to humans via the bite of an infected female Aedes aegypti mosquito. It has the highest incidence rate among communicable diseases, with 397.71 cases per 100,000 populations. According to World Health Organization, approximately 131,000 cases were reported in Malaysia in 2019. Therefore, mathematical models for dengue fever have investigated compartment dynamics using susceptible, infected, and recovered models, or most widely known as SIR models. The SIR model identifies 2 populations, which are human population and vector population. For human population, it is made up of 3 groups, while vector population is made up of 2 groups because once the mosquito is infected, they will not recover. According to the article that we refer, this is the original mathematical model of host-vector interaction comprising nonlinear differential equations involving several parameters. Next.
Dengue fever is a mosquito-borne viral infection that is endemic in more than 100 countries in the world. As stated in the introduction, since there is a significant increase in dengue fever cases in Malaysia throughout these years, we would like to study how does dengue fever spread throughout the human population. The state of Sarawak, which is the biggest state in Malaysia, will be the site of study for our research. To reduce the complexity of the SIR model, our project will focus on host population only. Based on the article that we refer, we modified the model by adding a new parameter, theta H, which represents the death rate caused by dengue itself. In the model, we applied the collected real data reported by Ministry of Health KKM in Sarawak, Malaysia in 2010. Our modified SIR model and its flowchart are shown in the slide. Next. To simplify our model, we divide all the differential equations by NH. Then we assume x equals to SH divided by NH, y equals to IH divided by NH, and z equals to RH divided by NH. So the differential equations in our modified model are now simplified in terms of x, y, and z.
So for the value of parameters over here, we have 4 parameters here, and we got their values from 2 of the sources over here. And then we can calculate the value for alpha by using the values above and also the value of beta. Next. So to calculate the number of infected vectors, IV, we will be using the article dengue fever surveillance. And we know that the total number of larvae found in the study site, which is TAB Kuching Sarawak, is 309 in the year 2020. And then we also find out the area of the study site, which is 0.65 kilometers square. Next. So by using the total area we found, we can calculate the number of larvae in the specific area, which is S is equals to 59.42 million. And hence, Sarawak has the approximately 59.4 million larvae, and then we can use it to calculate the number of infected vectors as shown below, and we got 5.3478 million. Okay, next. And for the identification of model, we have 3 equations over here, and all of them are ordinary differential equations, and they are first order, linear, inhomogeneous, and the type of coefficient they have are constant coefficients. And since the model is already in linear form, linearization process is not required. And then for the critical point, we all know that the critical point will occur while the value of dx dt, dy dt, and dz dt is equal to 0. So what we do is we substitute the value of parameters into these 3 equations over here, and then we equate them to 0, and then we can find out the critical point or the equilibrium point, which is 0.002765, 0.01346, and 0.9836.
Next, since we want to focus our attention on a single member of the infinite family of general solutions by specifying the value of arbitrary constant, therefore we do this indirectly by specifying instead a point that must lie on the graph of the solutions. By using the data at week 1, the initial conditions are x20 is equal to 0 is equal to 0.9999, y when t is equal to 0 is equal to 1.0319 times 10 to the power of negative 4. Z when t is equal to 0 is equal to 3.3992 times 10 to the power of negative 5. While for systems of differential equations, after we substitute the parameter values, this is the system of differential equation. In order to solve the systems of differential equations in our SIR model, we will use both Laplace transform and matrix method. First, I will explain about the Laplace transform. For dx over dt, we rearrange the equation into this and perform the Laplace transform, and we will get this. Then by using the initial condition, we get x equal to this. And then using inverse Laplace transform to get the solutions of xt, which we get xt equal to this. Next, for dy over dt, same steps with the dx over dt, we rearrange the equation into this, and then using Laplace transform to get this. And then since there is x in this equation, we substitute the x that we get from dx over dt and get this. Then by using the initial condition, we will get ys equal to this, and then using inverse Laplace transform to get the solutions of yt, which we get yt equal to this. Z over dt is also the same. We rearrange the equation into this, and then using Laplace transform to get this. Since there is ys in this equation, we substitute the ys that we get in dy over dt and get this. Then by using the initial condition, we get zx equal to this, and then using inverse Laplace transform to get the solution of zt, which we get zt is equal to this.
Next, I'll present on how matrix method is used to solve the system of differential equation. Firstly, we convert the system of differential equation into the matrix form. Then we'll make matrix A minus lambda with matrix identity to get its determinant. The determinant will be our characteristic polynomial. Next, the characteristic polynomial will then be equals to 0, and it becomes a characteristic equation. Then we will have to find all the roots, and those roots will be our eigenvalues for the system, as shown in the slide. To find the eigenvectors that correspond with the respective eigenvalues, we substitute all the eigenvalues in the form, and hence all the eigenvalues for the eigenvectors for each eigenvalues will be shown in slide. Next. And these will be eigenvectors for the second eigenvalue and third eigenvalue. Next. With the eigenvalues and eigenvectors obtained, we will place them into the general solution, and we will get three equations with C1, C2, and C3 being not found. So we have to insert the initial values and assume t equals to 0, and this will lead us to values of C1, C2, C3 as shown in the slide. Hence, place all the C values into the three equations, and we will get our specific solution as shown in the slide.
Alright, for the result and discussion, to check if the specific solution that we obtain from both Laplace transform and matrix method are correct, we substitute t equals to 0. Then, for both methods, we found that the value of x, y, and z with t equals to 0 is close to our initial condition, thus the specific solution that we obtain is correct. For stability analysis of SIR model in Sarawak, this is the equilibrium point. And these are the eigenvalues that we obtain by using matrix method. Since the eigenvalues are negative and all are real, the equilibrium point is a node, while the trajectories of the solution in the phase portrait will move into the equilibrium point, thus the system is asymptotically stable. In conclusion, since the system is stable, thus there is not any significant concern, and this indicates that all human populations in Sarawak are healthy, as there is no occurrence of dengue virus infection. Thus, the model shows that dengue fever is not significant in Sarawak. So that's all from our group. Thank you for listening and watching to our video.